previous seminar, you will have heard some of them, but I promise you that we will have some interesting updates. So first of all, we know internet technology is very important. It builds a connected world, and we have a lot of wonderful applications everyone knows. Okay, and privacy and authentication are very important, and because there can be a lot of sensitive data in the cyberspace, every day we might download some private data from some cloud or whatever, your bank server. Certainly, you don't want the adversary to be able to see your private data or tamper with your private data. And serious consequences are there. Many things could, if things go wrong, there can be a lot of serious consequences. Okay, an important technology to protect internet security is public key cryptography. So it is the foundation of HTTPS, which is used for our email, login, secure payment, social media, a lot of things. Okay, so you have implicitly or explicitly used HTTPS. Okay, and today there is a survey saying HTTPS is used even more often than the original non-secure version HTTP. Okay, so the foundation of the public key cryptography is we need some mathematical problems that are not solvable by even supercomputers. And very fortunately, or maybe you want to say unfortunately, we only have a few candidates, such as vectoring and discrete log. Vectoring, for example, I give you a very large number, and you tell me this n, big N equals P times Q, for example, 15 equals 3 times 5. But of course, 15 is just too small. If you have like a 10,000 digit number, okay, if I give you this number, it's very difficult to find its factors. And there is another problem called discrete log. Okay, so these problems are not just mathematically interesting. They have been widely used, okay? So if you know this RSA crypto system or Diffie-Hellman key exchange, those type of things, okay? We don't need to go into the details, but if you, there are a lot of softwares, secure communication, you can see those terms, okay? So because of the impacts, those authors have been awarded Turing Award, which is the Nobel Prize for the computer science, for their great contributions. Okay. However, this foundation of public key cryptography is challenging. So in 1994, Peter Shor discovered or proposed a polynomial time. So you can think of polynomial time as efficient quantum algorithm to solve vectoring and discrete log. Okay. So this means quantum is more powerful than classical computing. Okay, so if the adversary has the power of quantum, he can break all the public key crypto systems in use. And fortunately, the technology was not there. So in 2001, okay, 20 years ago, the best vectoring can be done by quantum computing is 15 equals 3 times 5. And certainly this is too small to break anything meaningful because your little brother, maybe elementary school, can solve 15 equals 3 times 5. That's easy. Okay, so not practical yet. So people were, okay, quantum, cool, that's a cool technology, but so what? Okay, but technology would advance. So towards building larger and larger scale quantum computers, for example, IBM and Google, we have this very interesting chart. So we can think of number of qubits as a measure of the scale of quantum computers. So it's like classical bits, 1 bit, 2 bit, 0, 1, something like this. So the unit for quantum computing is qubits. Okay, so 1998, we had 2 qubit system. And over the next, say, 20 years almost, we increased the number to 49. And in 2019, Google did this very interesting task. So they first proposed a quantum system. And this quantum system can produce some specific sampling task. And this task, Google said, for quantum device, it takes roughly less than 1 minute. But if you use supercomputing, it should take maybe more than couple years. Okay, so this is the first time we can demonstrate experimentally that quantum is more powerful than classical computing. Theoretically, quantum is more powerful, but who can do experiments? So in 2019, this is the first experiment, say, that can be observed by humans. Okay, 2023, we have more, and the projection, and by 2013, we want to build a 1 million qubit system. But of course, you know, those entrepreneurs or those researchers, they want to draw a big pie and say, hey, we can do this, but who knows? But no matter what, due to this trend, quantum attacks might become feasible in some foreseeable future, okay? So to face this new reality, NIST, National Institute of Standard and Technology, had this post-quantum cryptography standardization core since 2016. And industry had a lot of efforts for evaluate performances on post-quantum candidates such as Google, Amazon, etc. Okay, so we know technology, traditional public key cryptography is facing a crisis. They will become obsolete eventually at some point. So we need new security infrastructure. So this is a critical time to develop new sciences between cryptography and quantum computing. So particularly, we need new foundation for post-quantum cryptography and hopefully we can get some new crypto capabilities. So my research basically is aligned with this mission. So the basic one is we want to rebuild basic cryptography against quantum computing. And using this as a foundation, my vision is to enable richer crypto capabilities and a lot of fancy things, which I will talk about. Okay, so this including computing on encrypted data, application to private machine learning, data analytics, and numerous other advanced crypto designs. And those are terms or buzzwords, but I will explain them in more details. So for today, we are going to talk about some background and some recent progress and some challenges and my vision. Okay, so let's talk about some background. So cryptography in general, we want to ask two questions. So the first question is, what is security? And the second question is, how to achieve security. So what is security? Intuitively, you can think of no one can break the crypto system. But what do you mean by no one can break the system? And how do we achieve security? So there can be infinitely many possible attacks. So how can you argue that your crypto system can defend against so many possible attacks? So the modern cryptography is taking the following approach. So first of all, we need to define a very clear security goal. Okay, for example, we can consider building a secure channel. So this secure channel, you can think of there are two parties. Okay, so they want to communicate securely, and so this party wants to send private messages to the other party, but the channel might be listened by some adversary. Okay, so idea is to hopefully we can confuse the adversary. The adversary knows nothing by listening to the channel. So in order to do this, we need to define security. So what do you mean by the adversary cannot learn anything by listening to the channel? We need a mathematical formulation for this. Okay, so one particular idea is, so traditionally people thought this as the adversary cannot recover the whole plain text. But is this good enough? So if you have taken my cybersecurity course, you know this is not enough. So why this is not enough? For example, consider this message, okay? So if the party, say the Princess Leia, if she wants to send this message to the other party, but if the adversary can figure out only partial the message, this is already very, very bad, right? Because the adversary might figure out, okay, this message is delivered to Obi-Wan, which is bad. Okay, so in order to define security, we need the security to guarantee adversary learns nothing, including everything here, including the Obi-Wan. Okay, so how do we formulate this? We consider a mental experiment. So here there are two messages. So by listening to the channel, the adversary is totally confused. He cannot distinguish whether Princess Leia was sending the orange message or the blue message. Okay, so if we can achieve this, we can argue that the adversary learns nothing. So this is important. So this notion is not just theoretically interesting. It has been explicitly requested in the NIST post-quantum standardization code. Okay, so in order, if you want to work in this area, you need to understand this notion. Okay, so how do we realize the security goal? So as there is no really physically secure channel, so for example, these two parties might be far away in two different galaxies. So in order to do this, we need to use math to realize this physical channel. So you can think of this math as joy or encryption. So you want to throw this message encap this message in this joy. So this is all by mathematics. And by looking if the other party has the secret key, he can open the drawer and recover the message. But if for those who don't have secret key, he is completely confused. He doesn't know whether the drawer has an orange message inside or blue message inside. Okay, so that's the high-level idea. So how do we prove security against infinitely many attacks? So there is a beautiful framework called the reduction framework. We need three things. So one is math problem, and one is crypto system, and the other is reduction, or called proof of security. So this reduction framework says we want to prove that if an adversary can break the crypto system, then there exists a reduction that can solve the underlying mathematical problem. So if you can realize this, you can so the above statement equivalently would become the bottom statement. So if the math problem is not solvable, then no adversary can break the crypto system. Okay, so the crypto system is secure. So now we only need to focus whether this math problem is solvable or not. So for example, so we have some candidates. For example, RSA discrete log are those traditionally we have been using those two problems. And and then we can build crypto systems based on RSA. So as long as RSA discrete log are not solvable, the crypto systems are secure. But quantum computing can be viewed as this super like strong power attack. You can think of that as Death Star, which can kill RSA and discrete log. Okay, so this means the foundation is broken by quantum computing. So in order to build a new secure, say, foundation in the presence of quantum, we need new hard math problems, and we need new design and proof of security. So that's the basic idea, what's going on for the quantum computing and post-quantum cryptography. So let's talk about some recent progress. So NIST, as I said before, had this call since 2016. So we aim to standardize future post-quantum cryptography. So why do we want to start now, even if we don't have really like a usable quantum computer yet? Because one thing to keep in mind, if you want to migrate one system to another system, according to NIST, the previous survey, it might take more than 20 years, okay? So it's not like, hey, you click a button and everyone upgrades their system to the latest version. No, it's not like this. So it takes time. So if you go to a business, okay, if say a company hires you to help the migration, you will face a lot of questions, because people, those companies, they might say, hey, we don't want to change our code. We don't want to upgrade our system. If you upgrade our system, maybe there are a lot of bugs. We cannot deal with that. So that's why NIST says, say migration from systems to systems is very time consuming. Okay, so and another thing is we are facing a lot of challenges. For example, it's very hard to find plausible mathematical problems. Okay, how to define, how to set parameters for security and efficiency, how to implement, how to deploy, those are questions, a lot of questions. So we had better to start earlier. Okay, so we need, so first of all, the most important thing is we need more new mathematical problems, okay? So people have been considering several categories, like code-based cryptography, lattice-based, hash-based, and many more, okay? So the current progress, so last year, we just finished, so this basically is like this. So the first call for proposal, and you can submit for round one, everyone can submit. And NIST will eliminate, So up to the third round, which was just concluded, I think last year, okay? So 4 algorithms are selected for standardization, okay? And when they are selected, it doesn't mean like immediately we are going to use that. So still some further research is going on for them to become standards, okay? And 3 of them, okay, are from lattice-based cryptography, and 1 is from hash-based cryptography. And currently, it's now the ongoing effort is 4th round, okay? So 3rd round we have concluded, but most of them are lattice-based. So NIST is a little bit worried that we have put all the eggs into one basket. So 4th round, we need, say, to consider other, say, candidates, okay? And we can see there are a lot of things going on for the 4th round, okay? So let's talk about some interesting things, which I put this title as sleepless cryptographers. So there are many candidates broken. So in 2022, there is one candidate called Rainbow broken by some mathematicians. And this broken is not just theoretically broken. They implemented, they said, I can break this scheme using my laptop in, say, 1 weekend. So this is a really break. And another one is Psych, which was broken presented at Eurocrypt 2023 last year. So you should not really overlook those broken things because each scheme, so first, Rainbow and Psych, they have both, say both of them have advanced to the third round, okay? Almost before the announcement, okay? Did those schemes did the announcement of the breaking. And you know, there are a lot of research papers, including PhD thesis, okay, built on top of Rainbow and Psych. So my previous colleague, he advised maybe 3 students working on implementation of Psych. Okay, and very fortunately, those 3 students have successfully defended their PhD thesis just before the announcement of the break. Otherwise, it could have taken the students maybe 2 or 3 more years, delaying their graduation. So sometimes it's very hard to say. So that's why I'm saying if you want to be a cryptographer, maybe many times you will have nightmares, but that's fine. Okay, but still plausible. There are other candidates. Okay, so today I'm going to talk a little bit further about lattice-based cryptography because this is first very cool, and 3 candidates have been selected, and beyond those public key cryptography, we can, from lattice-based cryptography, we can do more. Okay, so what are they? So lattice-based cryptography is we build crypto systems based on some hard lattice problems, and there are a lot of advantages. For example, efficient operations and resilient to quantum attacks, and it is a foundation for many advanced crypto systems. So we need new hard problems if we want to work in lattice-based cryptography. So one problem, particularly important, and you really need to remember the name, is called LWE, learning with errors. And I will talk about this, in maybe like the next 20 minutes. So it has attract a lot of attention in theory and practice, and we can build new post-quantum candidates in theory, including public key encryption, signatures, key exchange, blah. And there are, 3 variants of LWE are going to be standardized by NIST. So this is a super important problem. So beyond public key encryption, LWE allows computation on encrypted data. What is this? So the buzzword is called fully homomorphic encryption. And it is important for outsourced computation. And according to an agency called DARPA, this FHE is holy grail to keep data secure while in use. So pictorially, we can think of this. So suppose a user, she can encrypt some sort of her data and outsource this data to the cloud. Because this data is encrypted, so the cloud doesn't know what's going on the data. But she can request compute F. So even though the server doesn't know what the data is, the server still can compute encryption of F of data, okay? Even though the server knows nothing about data. And she can decrypt and learn F of data. So this is fully homomorphic encryption. So what can we do with fully homomorphic encryption? So this is an elegant solution to Yau's millionaire problem. So what is this? So consider two parties. Each party has a number. For example, I have my bank account, your bank account. We want to compete who is more, say, you can say who is richer or who is poorer. Okay. But we don't want to reveal our input to each other. Okay. So in order to do this, Alice or the princess can encrypt her input, and then the server can just compute f of x, and the f is the comparison function, and then say the princess will know whether x is greater to y or not, but she will not learn anything about y. Okay, so this is a classical example, but there is a more modern say modern application. So consider the say the princess has some picture, and the cloud has some machine learning model. So the cloud wants to provide some service, and the user, okay, or the princess in this case, she doesn't want to reveal her picture to the server. So is this possible? So by using fully homomorphic encryption, this is possible. She just encrypts her picture, and the cloud can do a homomorphic data and analysis on encrypted data. So one very interesting thing about this is theoretically this is doable, but in practice this was very slow. Okay, so previously, if we want to do this, say previous research, if you want to do this inference of a picture, if you have heard about a data set called sidebar 10, so like there are 10 categories and each one has some like a sheep, dog, or whatever. So previously it takes, say roughly a homomorphic inference would be, say, more than 10 minutes per picture, okay? Or maybe like 10,000 seconds. So, but things have been, say, improved significantly, but from software and hardware. So, like an hour ago, I just submitted a paper. So this is by using, so we can achieve the like 50 seconds per image, okay, by using H100. So have you heard H100? Okay, that's fine. A100. Okay, no, GPU. Okay, GPU. And H100 is currently the state of the art of NVIDIA. So have you heard NVIDIA? Okay, so now it's their earning call. Okay, so if you know what's earning call of a company, you will see like that's something very interesting. But anyway, so by using NVIDIA GPU, the state-of-the-art GPU, we can significantly reduce the computation time from, say, couple minutes, maybe a couple hours to 50 seconds. And we believe that this number can be further pushed forward, okay? This is not the end. Okay, so, the triumph of crypto theory says, using, say, under LWE, we have post-quantum public key encryption. Under LWE, we have fully homomorphic encryption. And under LWE, we have a lot of things. But there is, so in place of LWE, there is a Gödel Prize, which is one of the most prestigious award for theory of computation given to the author. Okay, so the citation is, this is a super important problem, countless subsequent works, So what is learning with errors? Yes, so this problem, I think we still want to learn some technical things today. So you can understand this. So consider there is a box, okay? This box contains some secret vector, okay? And the user, if she clicks the button, she will receive a sample. A sample is a random vector A and A inner product with the secret S, plus some error. And she can do this multiple times. And at the end, she collects those vectors as a matrix A and those B's as a vector B, which is AS plus E. Okay, the goal is to find the secret vector S. So if you have taken elementary linear algebra, you know this. If there is no error in the picture, you can solve this by using elementary Gaussian elimination. Okay, I believe you have all learned this. But the thing is, if there is error in the equations, then even very powerful adversary, quantum adversary, cannot learn the secret. So, however, LWE constructions are not very efficient in practice because of large keys, large ciphertext, slow in computation. So how inefficient? That's something interesting. So we consider the original public key encryption proposed by Regev, the original work. If we did some calculation and we found the public key length needs to be 1 megabyte, okay? So 1 megabyte, what is this concept? So if you're going to compare the efficiency with pre-quantum RSA, so RSA, the public key roughly is like 3,000 or 4,000 bits. And 1 megabyte versus 4K bits, that's a significant, say, efficiency drawback. So in order to and so no NIST candidate really use this type of original public key encryption. So we know inefficient. So the research goal is how do we improve LWE? So because this is a very fundamental for public key encryption and many advanced crypto capabilities. So to improve efficiency, we need more algebraic structures, for example, using polynomial rings, using like some module structures. Those are mathematics, or using rounding and blah, blah, blah. So by using those techniques, we can significantly improve efficiency. But one fundamental question we want to ask is, okay, we can improve efficiency, but are those variants of learning with error taught? Okay, because if you do a little bit modification, crypto is very subtle and sensitive. So insecurity really comes from nuances. So in order to do this, in order to confirm the hardness of the variants, so there are a lot of works, and including my research. Some of my research is to show formally using ring and rounding is as hard as just using ring, the problem. So the prior work says the ring version is as hard as some ideal lattice problems. So those problems are technical. I'm not going to talk about them. But the logic is, by my result and the prior work, we can show that ring plus rounding is as hard as some ideal lattice problem. And so as far as we know, currently there are no known algorithms for the ideal lattice problems. So this means ring plus rounding is as hard, so it's plausible. So that's part of my work. Okay. So finally, I would like to talk about some challenges and vision. So the challenge is very interesting. So in the past 30 minutes, I talked about hardness of LWE, how amazing LWE when its variants are. But on April 10th this year, okay, a young researcher, Yilei Chen from Tsinghua University in Beijing, he claimed that a new quantum polynomial time algorithm that solves LWE. Okay, solving LWE in quantum polynomial type. That's April 10th this year. So at that time, on April 10th, I was at a workshop at NIST. So we had a lot of discussion on this work, and hey, whether this work is and about its implications. So, say intuitively, he proposed a 9-step algorithm, and this was posted on an archive, a public archive called ePrint 2024 555. So the implication is, so we know, say public key encryption signatures submitted to NIST are not really affected by this attack. But several variants of FHEs are not post-quantum secure because can be broken by his attack. Okay, so currently only the third generation of FHE still survive. So currently there are only 4 generations of FHE and only 1 generation survive. But if one can improve Ely Chen's attack, then maybe LWE is not secure at all against quantum. So there have been a lot of discussions. And later on, if time permits, I can show you a blog summarizing, and if you are interested, you can read the blog. There are a lot of great researchers from MIT, Stanford, and blah, blah, blah. So we had very intensive discussion about this. And on April 18th, okay, a fatal mistake was discovered by a student at Berkeley and also another, say, a very famous quantum researcher, Thomas Vidin. So they discovered the same mistake, and this is quite fatal and not fixable. So the current thing is LWE and their variants remain post-quantum secure. So this is just very, very recent. So now we can have 2 different views about this result. And so if you still believe LWE is hard, as most people still do, so we can do research. So maybe new algebraic techniques to improve speed, the security of public key encryption and fully homomorphic encryption. And we need new analysis of a security foundation and perhaps software and hardware acceleration. Okay, so this is LWE plus. So if you are more positive, sure. And if you are more negative about LWE, you still have research to do. And that research is called Make the Algorithm Great Again. And but we don't expect anything great again, like say by this November. But this is certainly a great opportunity for you to think about. Okay, so this is basically say either way. So which way do we really want to pursue? So it's hard to say hard to tell for me to tell you at this moment. But I would like to quote a famous word from Silvio Micali, which is a Turing Award winner for 2022. So if you remember, from the very beginning of the slides, I said security foundation was say formed by Goldwasser and Micali, and this is the Micali. Okay, so he said, science wins either way. Okay, so no matter which one is true, it advances the science. Okay, so if LWE is hard, it is hard, and we can enjoy everything it brings. And if it is not hard against quantum, and it is not hard against quantum, we cannot do anything about that. So this as long as we can advance science, then I think this is an important merit for scientific exploration. Okay, so basically, this concludes my talk. And finally, I want to share with you that blog, which has a lot of discussion for this. And if you are interested, you can read through the discussion. So let me do this. Share desktop. One. Okay. So we can see. Okay. So this is a blog by a professor called Scott Arison. He was a professor at MIT, and then he moved to UT Austin, so the University of Texas at Austin. So he is a famous quantum researcher and quantum computing researcher, and he writes this blog that captures a lot of great news in cryptography. And not cryptography, quantum computing, and certainly that Ely Chen's attack is some of his. It's very important, so he wrote a blog about that. Okay, and so you can go to the blog, and so as I said, before we go to that blog, you need to remember that sleepless cryptographers, and here, if say, his blog is a little bit interesting. So if you have dated someone who is non-IT researchers or non-IT major, maybe you will feel this, but either you are a girl or a boy, but anyway, so let's go to his, yes, this is the blog he's posting, and this ePrint 2024 5x5 is Ely Chen's paper. So because at that time, it's very hard for any cryptographer to sleep at that time, because that attack was too, if true, would be devastating. But anyway, so, okay. So that's basically my talk. Thank you very much.
Thank you. Time for a couple of questions. If anyone has a question. If no one does, I got one. What is there? So you showed that graph of the increasing number of qubits in quantum computers over time. At what point does that graph get to where quantum computing is expected to conquer all current cryptography? How many years ahead is that?
Okay, so let me reopen that. Okay, so okay, that one. So say there are some estimations. So first of all, the number of qubits, that's an important measure, but another important thing is whether you can control all these qubits in a coherent way. Okay, so you can, so for example, currently you can make 433 qubit system. You can easily duplicate 1 million times. Okay, but the thing is you cannot control all these 1 million qubits in a coherent way. And if you cannot control all these qubits, then you cannot deploy the quantum attacks. So the most difficult thing is to control all qubits simultaneously. And controlling all qubits, this is currently this is beyond our physics technology, because qubits are very, very, say, sensitive. So if there is a little change in the environment, you might destroy the behavior of the qubits. So it's very fragile. So there are techniques called the quantum error correcting code. So maybe like you can duplicate several qubits. So even if some of them are destroyed, maybe you can still proceed the computation. But this duplication would require way much more qubits. So by 2030, this 1 million, I am not sure how many qubits can they really control. Okay, so currently the most powerful thing that quantum computers can do, perhaps, is to simulate quantum mechanics. Okay, so the best thing you can do is to simulate itself. Okay, but on the other hand, this is a little bit tricky. If you ask those quantum researchers, they will tell you like, hey, fund us and like $billions of dollars, we can promise you the world. Of course, that's how researchers approach, say, congressmen or whatever. But currently, I'm on the more conservative side. I would say, let's see.
Questions? Okay.
Please.
Do you think that in the future, companies will look for people who know cryptography? Do you think that because in the article you showed, it wrote openness of OpenAI.
Uh-huh.
So do you think how will be the companies or in the future? What do you think?
Okay. So maybe we don't need to talk about future. We can talk about now. The thing is, companies, they do need, say, people who know crypto and security. So I wonder if you have heard a term called GDPR. GDPR. I cannot. So if you don't know GDPR, you can you can use your best friend, which is Google GDPR. So this is a general data protection regulation, and this is very important in Europe. So this regulation kind of says you cannot expose your client's data to maybe if you want to post advertisement, and you cannot say, hey, I have some other clients, I just sell the client's data to those, those other companies, or you store your data in in some other countries or in a non-regulated way. This is not okay. And this is particularly important in Europe. And Google and Meta, they are facing a lot of challenges in Europe. So they pay a lot of fines. So because they don't have a privacy preserving solution, so they think the best way to do this, to do business, is just to pay the fines. Say, who cares? We are rich. But if you could solve those regulation issues, privacy issues, then you can earn a lot of money. And there are startups doing this type of things, and those startups have become very I will not say successful, but they are in a very good trend. So because they can solve something Google and Meta cannot. So and this happens today. And also there are other other industry. Maybe you have heard about cryptocurrency, like a lot. So in order to do a secure transaction, we really need cryptography. And in the future, post-quantum cryptography will be deployed. Okay, so at some point, this transition will definitely happen. So So you know, in the future, the Congress will make a law that by the time of this, by this time, every operating system, everything needs to support post-quantum cryptography. Otherwise, you cannot do business in the US. Eventually, this will happen, but of course, this is not now. So if we know how, what process it needs to take for the migration, okay, then we will definitely see a lot of opportunities. Okay, so I'm not just saying like in the future, but I believe now.
All right, well, thank you very much, Dr. Liu.
Thank you.